Welcome to this third live interactive session for the NPTEL course, a brief introduction to microsensors. The course code for this course is NOC24E09. The course instructor for this course is Professor Shantanu Talukdar, Assistant Professor, Department of Electrical Engineering and Computer Science from ICER Bhopal. My name is Amit Ugle. I am a PMRF Prime Minister Research Fellow in Department of Mechanical Engineering, IIT Tirupati. I'll be the tutor for this course. So this is we are discussing the syllabus and the content related to third week. So before we begin, just a few formalities. So it is a live interactive session to boost your performance. It is not compulsory, but we highly encourage your presence. You are requested to be respectful in the chat. If you have any questions, you can unmute yourself right during the question when the question is being discussed, or you can wait till the end and discuss later. Other thing, questions, you can ask your questions related to the coursework or related to assignments at the end of the session. As always, the videos will be uploaded on YouTube. This is the link for the YouTube channel, and you also have the access to the page where you can actually access the video links. So today's session plan, basically we'll be revising some important concepts. We'll be discussing the practice assignment 3, and then we'll be moving into the question and answer session. So this is a course outline. This is a 4-week course, and we are right now in the third week. The third week mainly goes into silicon and its properties, microfabrication, and lithography, the process as such. So let's move to the revision of important concepts. So before that, we'll just ask you, do you know why MEMS came into existence? Like, why? Oh, I think there's nobody attending here, so I think most of the people will be watching this the recorded version on YouTube. So I'll just go in straight away. So basically, we all have heard that the original computers usually used to have take a big size of a big room per se, or even everything in earlier time was quite big in size. So everything would take a lot of space. Even for that example, even your television screens used to take a lot of space, but now they have all shrunk in size. So basically, the process of shrinking everything in size is called as miniaturization. So the person who is responsible for this revolution of miniaturization is the person you are watching on the screen. This is Professor Richard Feynman. He gave one of the lecture in 1959. So this is 1959. This is a visionary person. Everything at that point of time would be big, and nobody would have thought of something that can shrink everything to a small size. So for that, the first person to actually think of something shrinking it down is this person, Richard Feynman, in his lecture Plenty of Room at the Bottom. So he is a Caltech professor. He is a former Nobel laureate in physics, and he basically came up with the idea that we can shrink everything down, and that is the here the bottom stands for the scale less than the millimeter range. So millimeter, micrometer, nanometer, in that range. So uh, that's that's the term what we meant by bottom. And he came up with that visionary idea that we can shrink everything down and miniaturize everything, and that has actually led to a big revolution. Everything around the world has shrunken in size. The computers which used to take big rooms in the previous century can now even fit in your hands, in the have more had less computing power compared to the mobile phones which currently just fit into your hands. Everything was shrunk into size based on this visionary man, Richard Feynman. So So now we know who actually came up with the idea of memes. So basically, how do we make memes? So do we have any idea? So for making memes, we need a room called as clean room. So here we are having a room wherein the biggest enemy of of the process is dust, because dust can actually spoil the entire process. So from that we realize that uh, we developed a room which is called as a clean room, which can so really sorry for this technical problem. So I'll restart the session. Welcome to this NPTEL session for welcome to the live session for this welcome to this live interactive session for the NPTEL course, a brief introduction to microsensors. The course code for this course is NOC24 slash EE09. This is the third live interactive session. The course instructor for this course is Professor Shantanu Talukdar, Assistant Professor, Department of Electrical Engineering and Computer Science from ICER Bhopal. My name is Amit Ukle. I am a Prime Minister Research Fellow in the Department of Mechanical Engineering, IIT Tirupati. I'll be the mentor for this course. So I hope I'm audible and my screen is visible.
Yes, sir.
Yeah. So I'll just start with the session. So before we begin, just some sort of formalities. This is a live interactive session to boost your performance. It is not compulsory. It is highly encouraged. Be respectful in chat. You can ask your questions by unmuting yourself, because there are very few people attending live, and you can ask the questions at the end of session, and videos will be likewise uploaded on YouTube. You will get the link from the public sheet from your NPTEL portal, or else you can also go through this channel link as well. So today's session plan is basically we'll just revise some important concepts regarding MEMS and microfabrication. Then we'll discuss the practice assignment 3, and then we'll move to question and answer session. So this is the course outline. This is a 4-week course. We are right now currently in the third week. It is the content for this week is silicon and its properties, microfabrication, and lithography. So let's move to the revision of important concepts. So MEMS or micro sensors or something is the topic of this course. So what is micro, and who came up with the idea of micro or MEMS or this concept? Who came up with this entire concept is something you might have always had a question of. So the entire concept basically came from this person. This person's on your screen is Professor Richard Feynman. He was a professor at Caltech, USA. He gave a lecture in 1959. You can see the date. There is a plenty of room at the bottom. So bottom, basically by bottom he meant the scales below centimeters. So it is in the millimeter range, micrometer range, or the nanometer range. That is where he was saying that there's a plenty of room at the bottom. So he basically came up with the idea of miniaturizing everything, that is shrinking everything down. So earlier you might have heard from many people that the computers would take up the entire room per se, uh, and but they didn't have enough computing power. So basically he came up with the idea of MEMS that would shrink the entire thing down. So basically the computer which would take the entire room in the 1950s had lesser computing power than the mobile phone which you are holding in your palm. So that is the beauty of miniaturization, and that is what this person is the main person responsible for it. So where are these MEMS actually fabricated? So these MEMS are actually fabricated in a clean room. So clean room, as the word suggests, is a room wherein there is no dust, because if there is dust, the entire lithographic process will be interrupted and there will be a problem. So the entire process of MEMS fabrication actually takes place in a clean room. So clean room has everything. So it has, you can see here, there is a gray room. Then you have to wear the PPE kit. You'll The dust will be taken away from your body using this vacuum kind of structure. Then you enter into the clean room area. So here the airflow will be designed such that the dust is minimized to the maximum. Your movements have to be controlled. Even since you will be in a PPE kit, you will not, the dust that is generated from your body in form of hair falling or some other things will not come into play. So that is how a very sterile and a dust-free environment is created in a clean room, and that is what the clean room is meant to do. So there are two types of main design of clean room. So there is bay chase layout. So here what happens is, in the in this kind of format, what will happen is there will be one bay where the from where the wafer will come in. So one bay will have the photolithography process, that will be the spin coating or dip coating, whatever. In the second, there will be etching process. In the third, there will be deposition process, that will like PVD or CVD, that process. And again, there will be other processes such as the instruments, wherein the entire analysis is done. So that way all the areas will be separated and depending on the need. So basically the instruments don't need a very high amount of cleaning, so they'll be designed in one corner. And in some cases dust will be generated from the process. So like in terms of etching, dust is generated from the process. So in that so to eliminate that from affecting the other processes, they'll be separated from each other using a bay kind of area. In the other one is a ballroom layout. So in this, everything will be in one room itself. So all the processes will happen simultaneously in one room. There'll be in this layout, basically the movement of a person is very limited. Since everything is nearby, a person can do everything in one room. The movement is limited. So in that way, the dust can be reduced. But again, this is it completely depends on what are your requirements and how the what your process demands. So in some cases the bay chase layout is good, in some cases ballroom layout is good. In most of the research kind of facilities, ballroom layout is what is used in so basically, coming from the clean room, in the clean room basically we fabricate the MEMS devices. So MEMS device basically has transistors. So the entire circuit, or the entire, even your what do you say, the processor in your PC or your mobile phone has a processor. And basically the processor has transistors, and transistors are designed in such a way that you achieve computing from those transistors. So the number of transistors, the higher the number of transistors, greater is the computing power. So the number of transistors per in one square micrometer in a processor is defined by the Moore's law. So basically it says that the number of transistors in per square micrometer in a chip will double every 3 years. So here you can see every 3 years the number of transistors is doubling, and it will go on doubling till the future. So basically 4004 microprocessor in 1971 had 2250 um, transistors. A Pentium 4 processor that was in 2000s had around 4 million 42 million transistors. So you can see in the span of just 29 years, the number of transistors has increased so much. So that is how Moore's law is. So now basically the number of transistors has reached so high that the people are believing that Moore's law might not work in future. But as of now it stands. So these are the things. It may not come in your exam, but these are the things it may be asked in your interview. So just keep a note of these questions whenever you are listening. So yeah, coming to a basic MEMS fabrication process. So basically, if you in a layman's language, if how MEMS fabrication will occur is, first you will have a silicon substrate, then you will grow an oxide layer on it. So after you grow the oxide layer, you will then you will deposit the resistor material, then through photolithography, then you will pattern it, basically etch it out, and then you will deposit another layer of some insulating material or something like that, and then you will undergo these steps again and again till you achieve the final product which you want to achieve. So this is how a basic MEMS process actually looks like. So now coming to the MEMS process, the first thing is a substrate. So basically, how is a substrate actually made? So basically, even making a substrate is a very complicated procedure. It has to be a single, so the entire wafer which you are having has to be a single crystal, else you will not get the desired if there is high anisotropy in the entire structure, you will not get proper electronic components from it. So for that, a process is called, this is called as Lozarki process. So here what we do is we have a silicon melt. So in that you put a seed and then you just pull it, you go on pulling it up, and then you'll get a polysilicon rod, and then you will just dice it. So even making, so um, you can melt any type of silicon from anywhere, but you have to melt it in a pool. So you can't just directly make wafers from through any process. So to make wafers, this is how the process is actually followed. So you melt the entire silicon and then you just pull it up and then you dice it. So this is called as this is the process for wafer fabrication. So again, as I said, if it has anisotropic, it will be a problem. So to understand that, we need to first understand how the silicon's crystal structure is actually. So basically, it has a very closely packed structure which has 8 atoms in one unit cell. So it has two families of plane. It has 110 family plane, and it has 111 family of planes. Through it, it has two unit cells that are combined into one, each wherein they are being shifted by 45 degrees. So this is how you have to the families of planes look like, and this is the if you want to find out the angle between the two planes, this is what the formula is. Basically, u1, u2, u3 are the intercepts. So now we know that silicon is basically doped in different type. So it can be p-type doping or n-type doping. So and it also has different crystallographic structures. So basically, when an engineer is designing a device or making a device, he needs to know what kind of wafer is he being given. So uh, to do that and to ensure standardization, there are these the wafer, the silicon wafer is cut in such a way that it will be easily able to, the engineer will be easily able to visually see and identify what kind of wafer it is. So it can be if it is only one side is flat at the bottom, it is a p-type 111 wafer. If it has a flat bottom as well as a flat a 45 degree, it is a n-type 111. If it has um, flat bottom as well as a flat surface at 3 o'clock, it is p-type 100. If it has a flat bottom and a flat top, means at 6, and at 12 o'clock if it is flat, it is a n-type 100 atom thing. So as we said, after the substrate, we'll come into the growing of the oxide layer. So to grow oxide layer, basically you just have to oxidize the wafer, but it is not as simple as what you can see in normal uh, s- chemistry. It involves some complex reaction. So basically it uses a dry oxidation process or a wet oxidation process. Basically the process is the same, process is similar. So basically it uses nitrogen and oxygen. In dry oxidation there is only air is what is responsible for carrying out the entire process. In wet oxidation, the steam is used as a catalyst. So basically from this you can find out that in dry oxidation is a lot slower compared to wet oxidation. So if you want to get a very thin film, you use dry oxidation. If you want to get a somewhat thicker oxide film, you use wet oxidation. Pyrogenic steam is a type of um, uh, wet oxidation wherein just the input catalyst is hydrogen rather than using entire water per se. So now coming to the lithography process. So basically what happens is, after you have gotten the wafer, you have oxidized it, you need to pattern the you need to put the photoresist on it so that you can actually develop structures on the substrate. So for that you basically use the spin coating mechanism. So basically here there is a chuck, and on that chuck you basically place your silicon wafer, and then you just put the photoresist in such a way that it completely spreads on the wafer. So depending on the velocity, depending on the speed at which you put the resin, depending on this place at which you put the resin characteristic, the uh, coating characteristics per se, we can say will change. So the layer what we can achieve will be different, and how the layer will look like, we can see in the center there are how the layer will look like will also differ depend on all these characteristics. So it is very important that all these the important parameters are being noted and found out. So basically all these things are basically dependent on your experience. So you actually need to um, work with a particular photoresist to find out what will be the exact parameters for that particular resist. So then after you do all the all the resist coating, so you do the photolithography. Basically you use a mask and you pattern a structure on it. Then you wash off the excess area which has not been hardened. After that you undergo etching. So basically there are two types of etching. So there is wet etching and dry etching, or you can also call it isotropic etching and anisotropic etching. So anisotropic etching is where etching occurs in all directions. Basically here in this figure you can see that after photolithography, basically one space was left open so that that can be etched on from the wafer. So for that it was used, and then wet etchant was used. But here what is happening is the etching is happening in all directions, so it is called as an isotropic etching. In the anisotropic etching, basically the etching happens only in a single direction. Basically this is called as the dry etching, or it can also be called as the reactive ion etching or deep reactive ion etching, which is called as the Bosch process. So basically it's a lot of complications in that. So I would suggest you actually go and watch videos regarding this type of etching. So just giving you a basic overview of what these terms are. So in terms of actually wet etching, basically you need to find out what are the etch rates. So if you end up etching for more time, or if you put a very high concentration of etchant, it will just pierce through your wafer. So basically your wafer is very small in size. So you have to ensure that you put the right amount of etchant for right amount of time at right, so that you etch the right amount of material that you need to remove. So for this is the HN triangle, which is actually in practice. This is the very famous, very commonly used recipe, that is hydrofluoric acid, nitric acid, and acetic acid. So depending on the concentration of each of the material, you will get different H rates. So if the concentration of so nitric acid is kept constant at 70%. So depending on the percentage of hydrofluoric acid and acetic acid, you get different H rates. So so as you can see here, the chemicals are used which are fairly toxic. So these are nitric acid, hydrofluoric acid, acetic acid. These are highly toxic in nature. So basically, to eliminate that, we are using some other kind of agents which are called as tetramethyl ammonium hydroxide. So this is an organic agent. So this is highly selective. This you can achieve anisotropic etching, a sort of anisotropic etching. You can't with wet etchants. You can't achieve 100% anisotropic etching. To achieve anisotropic etching, you have to go with dry etching only. Um, so you have to go with dry etching only. But this is quite better. It has low toxicity compared to the other chemical etching. So this is also quite widely used etching process. So now coming to the last process. So basically you have done the etching, you have done everything. So now you actually want to coat something, right? You have made the basic things, but now you want to coat the. So basic thing is you have to make the substrate. Silicon is a semiconductor. You need a conductor also to actually achieve the connection between the all the transistors per se. So for that you need to coat materials. So to actually coat a material, you need a sputtering process. So basically what happens is you have argon gas. It hits the sputtering target, and then from the sputtering target, the atom atoms are ejected, and then they hit the substrate, and then they are deposited on the substrate. So this is how the entire MEMS fabrication per se work. Then the other following process involve dicing of the wafers and many other steps. But these are the basic steps which happen in MEMS processing. So till now, do you have any doubts regarding the MEMS processing, or
No.
regarding clean rooms or anything? Okay, I'll take this for no, and I'll move with it. So basically, so we come with the practice assignment. So the first question is, what will be the angle in degrees between the 121 and 110 plane? So whether it will be um, 54.7 degrees, 75 degrees, 30 degrees, 45 degrees. So basically, this is a trick question because 54.7 is basically used at lot of places in MEMS. So a person who is not paying attention to the question is bound to actually take 54.7. So be careful in mind. Actually use the formula which I have given earlier and try to solve it. So anyone has the any answer? Okay, so we'll actually move. Find it. I'll tell you the answer. So basically, as I've told you the formula earlier, so you have to use that formula. You have the U1 stands for the intercept. U1, V1 and W1 stand for the intercepts for plane 121, and U2, V2 and W2 stand for intercepts in plane 110. So basically, in case of U1 you have to place 1, in case of V1 you have to place 2, and in case of W1 you have to place 1. Again same thing, you have to do it. Then you will get cos inverse root 3 by 2, which stands for 30 degrees. Great. So any questions? Okay. In case you have any questions, just unmute yourself. So this is the second question. So which of the following is an isotropic etchant? So isotropic, basically, as I said, it etches in all the directions. So whether it's a 30% KOH solution, HNA etchant, EDP etchant, and TMAH at the EDP at 1150 degrees Celsius, or TMAH at 700 to 900 degrees Celsius. Basically, all these are wet etchants, so these will be an isotropic in nature. But here, what is being asked is which one is the most isotropic in nature. So basically, which has no selectivity. So KOH basically has plane wise selectivity. TMAH similarly has plane wise selectivity. So basically, how the crystal structure of silicon is, it has some kind of selectivity. So there is only one etchant which has no selectivity at all. It will etch any plane, any plane without any. So as I showed you in uh, the in the etching diagram, so there we had hydrofluoric acid. This is HNA, doesn't stand for hydrofluoric acid, but the mechanism is the same. So irrespective of any plane which is being used, it will etch in a consistent manner. So that is why it is called as the isotropic etching. So here we have HNA etchant as the isotropic etchant. So any questions? Okay, so moving to the next question. So basically, we have to identify the correct statement. So in this, the first statement is basically boron doping concentration at certain region can be increased so that those region will act as a mask and will not be etched away, and the structure like diaphragm and cantilever can be obtained, and there is no KOH etching along 111 direction of single crystal SiO2 using KOH solution. So we have to say whether so we have the options are whether only one is correct, only two is correct, both 1 and 2 are correct, and both 1 and 2 are wrong. So any guesses? Yeah. So in the first statement, which we'll go to the second statement first. So in the second statement, you can see that KOH basically, as I said earlier, the etching will always happen in case of a wet etchant. Just the etching rate will be different. So in case of KOH, in 111 direction of a single crystal, there will be etching. So you can, as you can see in this structure, there is etching happening where the KOH is being etched. Actually, in terms of 100 plane, the etching is quite slower compared to the 111 plane, but the etching will occur. And coming to the first statement, boron concentration can be increased so that the regions will act as a mask and will not be etched away, and structures like diaphragm and cantilever can be obtained. So basically, to develop something like diaphragm and cantilever, we want a very thin film. So that should not be etched away. So what boron does is boron acts as a like it acts as a blocker to think it packs it out. So if you increase the boron concentration, there will be less space for the etchant to actually penetrate. So if there is less space for etchant to penetrate, there will be less etching. You getting my point? So if you increase the boron concentration, it will act as a blocker to the etching. So basically, it will occupy so much, and there will be so much of holding between the atoms that the bor that the etchant will find it difficult to penetrate, and the etch rate will be slower. It will not happen that etching is not happening. Etch rate will be slower, but that slower etch rate will help in getting the structures like diagram, which are very thin in nature. So the statement 1 is correct and statement 2 is wrong. Any doubts?
No, sir.
No. So we'll move to the week 3 previous year questions. So basically, as I said earlier as well, we are not supposed to solve this year's question. So we'll be solving previous year question. This might not be your assignment question, but this will you can consider them very important for previous year for your end sem exams. So the final exam. Sorry. Um, so yeah, here it is. Here they have a device. Basically, they want to the cantilever has dimensions of 200 micrometer by 50 micrometer by 20 micrometer. The sacrificial layer is made of 250 micrometer SiO2. The etching solution being etched has a etch rate of 25 micrometer per minute in vertical direction and lateral etch rate of 2 micrometer per minute. What is the minimum duration of etching required to release the cantilever? Do not worry about the anchor. So you have to calculate. So these are the options: 18 minutes, 10 minutes, 12 minutes, 13 minutes, 25 minutes. Not enough information. So anyone can take any guess for this. This is quite a interesting question. Can you just take any guess on it? Even if you don't know the answer, can you just take a how will we approach it? Like how to approach this question? Can you just give me a idea? Okay, here we have two H rates. So we have the vertical H rate and the horizontal H rate, right? Lateral H rate. So for the cantilever to release, so basically we have the cantilever which is stuck to this wafer. So for the cantilever to release, we need to etch away the sacrificial layer. That's all we need to do. Once the sacrificial layer is moved away, we the cantilever will be released. So we don't need to actually care about the vertical H rate. We only need to care about the lateral H rate. So from now, you know which H rate you need to calculate. So now, what will be the distance? So just take an example here. Uh, we uh, we have dropped an agent on the right side, and you have dropped the agent on the left side as well, and from both sides the etching is happening simultaneously. So now the width of this device is 50. So since the etching is happening from both sides simultaneously, this person will eat away 25 micrometer. This agent from right side will eat away 25 micrometer. The agent from left side will eat away 25 micrometer. So basically, what we need to calculate is how much time is required by an agent to eat away 25 micrometer in the lateral direction. So you know the H rate, you know the uh, H distance. So can you just calculate the time? So you know the width as I explained will be 25 micrometer because the agent will be acting from both the directions. So the width which needs to be etched by agent from one direction is 25 micrometers since it's double. So the time will be half. So width will be half. So it's 25 micrometer and the H rate in lateral direction is 2 micrometer per minute. So the total duration which we need is 12.5 minutes. So since 12.5 minutes is not given, we'll consider the answer as 13 minutes. So did you get the answer? Did you understand it? So
No, sir. Can you repeat once?
okay. So you have this device, cantilever device, right? So here you have a cantilever device and you have a sacrificial layer. As you can see, my follow my pointer. So basically you have this cantilever device. So all you need to do is to release this cantilever device. So basically what you need to do is basically you need to remove the sacrificial layer which is beneath the cantilever. You understand till this point? So you need to release the cantilever, you need to dissolve away the sacrificial layer. So dissolving is basically etching. So this is to remove this layer. What you need to do is basically you need to put the etchant. So the etchant has etch rate of 25 micrometer in the vertical direction and 2 micrometer in the lateral direction. So here what you are doing is you are basically since you will be putting the etchant from the vertical direction, but what you need to do is you need to etch away the lateral area, right? You are understanding, you need to etch away the area beneath the cantilever. So you need to etch in the lateral direction. So the etch rate which matters to us is the lateral etch rate and not the vertical etch rate, because we need even the etchant will come from the vertical direction, what we care is how much area it removes from the beneath the cantilever. To calculate the area beneath the cantilever, we go with the lateral edge rate. Now the thing is, the um, can you just mute yourself for a moment before? Can you
Hi,
just
yes, it's clear, sir.
yeah? So now you, since it's etching from both the sides, it will just divide the width into two, and likewise from that equation you will get the time. So you just need to like visualize the scenario and you will get the answer. Okay. So coming to the next question, basically this is a straightforward question. Sputtering rate depends on. So basically, as I said earlier, we to quote we use the sputtering mechanism. So what will the sputtering rate depend on? The applied power, reflectivity of the material, melting point, substrate target distance. So actually, it will depend on both the applied power and the substrate target distance. So basically, if the power is less, whatever electron that is being ejected will not reach the substrate only, or very few electrons will, few atoms. Basically, what we are doing is basically we are applying power on argon. The argon is hitting the target material, that might be gold or silver, and then it is going up and hitting the substrate. So if the power is less, power in the argon is less, it will not actually reach the substrate. So or very few amount will reach the substrate. So that is the applied power. So the applied power is an important factor, and the second factor is the substrate target distance. Again, if the substrate is very far away from the target, not all the atoms will reach the um, not all the atoms will reach the substrate. So again, that will affect the um, overall sputtering rate from the process. So any questions for this?
No, sir.
Yeah. So we'll move to the next question. This is fairly fundamental. There is no, like, again we discussed this question earlier as well. So which of the following is N111 N type wafer? So basically be careful, understand everything, remember these things are very confusing, so keep that in mind. So 111 basically P type 111 is basically only one flat at 6 o'clock. N type is basically 4 to 5. So N type 111 you can remember as 4 5. Then p type uh, 100 you can remember as 3 o'clock, and uh, p type 110 you can remember as 12 o'clock. It is basically, you need to find your own way to remember things. This is how I remember it, so you can remember whichever way you want it. But this is that is these things are very important to remember, because these things will be asked in the exam, and these things are very confusing. So this is the answer for this. The answer is C. So basically you have a flat and you have a 45-degree. So that is how n type 111 looks like. So now coming to the fourth question, how many atoms are there in the unit cell of silicon? As I discussed earlier, the answer is 8. So basically it has, silicon has a very high packaging, so it has two unit cells basically combined together, and you are get packed together, and you are getting 8 unit cell atoms in one uh, um, 8 atoms in one unit cell of silicon. It has a very high packing efficiency. So any questions? So these are fairly about remembering. So no, the answer is not B. Answer is C. You have Okay. So basically, what happens is silicon is basically a closely packed structure. So it has sp3 hybridization is what occurs in silicon. So like silicon, uh, so what happens is it has one unit cell. So one unit cell with with normal simple cubic unit cell. So what happens is, because of the sp3 hybridization, there are two unit cells which get merged together. So you may consider it as a FCC. It is not a FCC structure. Basically, when you have an FCC structure, yeah, that is not how it looks. So this is basically because of sp3 hybridization, two unit cells are converged together and make into one. Because of high compression, high packing factor, they compress into one, and then you have two unit cells that are um, together. So at 45 degrees from each other. So basically this is how the SiO2 atom looks, and somewhat it is difficult to imagine, but this is how it looks, and you have to basically visualize it and understand how we came at this answer. So basically this is how it is. So I hope I've cleared it. If not, I'll try to put the visualization aid for the silicon atom. That will help you more in a better way, because this is the thing. Even it took me a time as well. So there is one tool for visualization. I'll put that in the description of the YouTube video, and you can just use that applet to actually play around and find out how the silicon actually looks. So I'll try to put that in this in the description section. So we'll move to the next question. So which are the commonly used p-type dopants? So we always know we have p-type dopants and the n-type dopants. So basically uh, p so we have boron, lithium, indium, thallium. So basically the answer here is, so for p type it is boron. So basically p type, the holes are what is the charge carriers. In n type semiconductors, electrons are the charge carriers. So basically in terms of p type semiconductors, they have 3 electrons in their outermost orbit. In terms of n type semiconductors, they have 5 electrons in their outermost orbit. So p-type semiconductors are basically the elements belonging to the boron group, which is the boron and indium. And n-type is basically phosphorus, are the elements that belong to the nitrogen group, that is phosphorus, nitrogen, etc. So this is fairly known to everyone, so we'll just move to the next question. So yeah, so the next question is basically HNA agent comprises of hydrochloric acid, nitric acid, acetic acid, sulfuric acid. So we had this. I discussed about this earlier as well. Can anyone take a guess? So yeah, so HNA basically has all the three: hydrochloric acid, nitric acid, and acetic acid. It's a mixture of all the three acids that is used for etching. So it can achieve very high H rates, and it can also be used for, since it is also highly isotropic in nature. Basically, it can etch anywhere, anything, because it's you can see here there are three very strong acids that are being used here. So it achieves high H rate, as well as it can etch out in a isotropic manner in all directions basically. So again, this is a fundamental question. So etching rate is maximum along which plane? So again, this is basically when will etching. So basically, to understand this, what will happen? I will just ask you one thing. So when do you think will etching rate be high? If there are too many atoms obstructing the etchant from entering, or will there be etching rate will be high if there are very less atoms obstructing the etching. So obviously, when the atoms are not closely linked to each other, the H rate will be very high. If they are far away from each other, or they are not very closely packed, the H rate will be very high. So yeah, so the answer here is 110 plane. In the 111 plane, there, if you actually see the, I'll show you in the earlier slides. So basically, if you see in the 110 planes, there are not, the atoms are very far away from each other. You can see from this projection, see, you can see this one edge, one side of a rectangle is the 110 plane, whereas in the 111 plane, it has this triangle. You can see from your on your screen. So basically, in this, there is a very less obstruction to the etchant to flow. So the atoms are very far away from each other. They are not very closely held together. So that is why in the 110 plane, the etching will be faster compared to 111 plane. We even had this in one of our previous answers as well. So here you can see 110 plane is the flatter plane, and 111 plane is the cross plane. So you can see here the etchant is moving faster in the straight direction, but in the cross direction of 111, the atoms are blocking it. So that is why the etching is happening slower compared to the 110 direction. So the straight, you are seeing that the etching is happening very fast, but in the cross directions where the 111 plane exists, the H rate is quite slower. So that is why it is there. So I hope I was clear with the explanation for this H rate.
Sir.
So moving to the next question. So
Yes, sir.
resolution can be achieved by photolithography is limited by. So basically, resolution is basically if you have something, if there are two objects. So basically, how well you can separate the two objects visually is what is the resolution. So if the objects are too small, so if I keep instead of having my two fingers, if I keep my two hair if I put like this, and if I stand, it will be very difficult for you to actually separate them using your naked eye. You will need some kind of zoom or something like that to actually separate them. So how well you can separate two objects is what resolution actually means. So what will the resolution depend on? So whether it will depend on the wavelength of light, intensity of light, time of exposure, or none of the above. So what do you think will the resolution depend on? So will it depend on the time of exposure? No, right? It will how much time ever you see this, like if you see this fingers, whether you see for 1 second or whether you see for 10 minutes, you can easily separate them together. Intensity of light, no, again, whether it is like light, um, yeah, whatever be the intensity, you can actually uh, you can easily separate out the two objects. But in case of wavelength of the light, basically it plays a very important role when you do it, because if the wavelength is very high, so what will happen is it will not pass through very small holes if it is there. It will not pass through very small features, because what will happen is if this a hole is small and the wavelength of light is quite big, it will not actually pass through the small holes. So the small features will not be achievable using the light of very large wavelength. So that is why the only factor which will affect the resolution is the wavelength of light. So any questions regarding this content, regarding the assignment? Any questions? Okay, so if you don't have any doubts, you can leave the session. I'll just keep the question session open for the latecomers. But if you don't have any doubts, you can just leave the session. So, in case you have any doubts, if you want to discuss something else, if you have any problems, because this is the second last session. So, if you have any problems regarding your research or something, I can maybe help you now, or maybe help come up with the answer in the next session, because after this there won't be any session. So this is the second last session, so next session will be the last session. So whatever doubts you have, please like something not related to subject, but something related to memes or per se, so you are free to ask me. So the people joining now, so we did a brief introduction to whatever the content was covered in this week. We I just gave an overview of all the concepts, and then we discussed the practice assignment 3 as well as previous year questions. You can access all these questions on YouTube through the public sheet. Even the course slides will be whatever the slides which I used today will be available there. If you have any questions regarding the week content or any other concept, you are welcome to ask now, or else you can continue with your work, because I'll just be keeping it open for the latecomers. So I'll just skim through the slides of today. So for the purpose of the latecomers. So basically we went through who is the inventor of MEMS, or from whom the idea of MEMS stems from. So basically, this is the Richard Feynman, and the idea of MEMS, and basically the idea of miniaturization came from the his lecture in 1959 at Caltech. There is plenty of room at the bottom, so this is a really fascinating lecture. If you have time, please have a look at the lecture. It is freely available on YouTube. And then we discuss about how clean room is. So basically, clean room is basically the room which doesn't have any dust or dust particles. So basically, the main thing is, if you have dust particles, since the features are as small as the dust itself, so the features which you achieve in MEMS are basically in micrometer range, which is equivalent to the size of dust particles. So that is why dust particles has to be eliminated as much as possible. So this is how a typical clean room looks. Actually, it has a gray room wherein you put in your PPE, and basically something like a vacuum cleaner which just takes away all the dust from your that is stuck to your PPE kit. Then you move inside the clean room. You have a PPE kit, so all the dust that is generated from your biological cells is eliminated, and only some of the like dust is generated because from whatever movements you undergo. And even the airflow is designed such that the dust sticks to the bottom, and it doesn't actually come up and exploit the affect the process. So these are the types of clean rooms, how the clean room actually looks. So there'll be benches setup, or a ballroom setup. In a benches setup, there is the um, base, so all the different processes are separated in base. So there'll be one for photolithography, one will be for etching, one will be for sputtering, another the last one will be for characterization. So that this is how a benches model looks like. Ballroom model, basically everything is there in one room. So basically it's a small clean room. Benches is for big clean rooms. So both kind of layouts are widely used depending on what is the purpose. In places like Intel or AMD, a pages layout will be used. In small research facilities, a ballroom layout will be used because that is cheaper to build. So again, we come to the next topic, that is Moore's law. Basically, Moore's law is a very important law when it comes to MEMS. So basically, it says that in the number of transistors per square micrometer will double every 2 years. So it's a very simple law, and here what we have done is we have found out how the Moore's law um, has worked in terms of Intel processors. So basically, in 1971, the 4004 had just 2250 processors, 2250 transistors. So now Pentium 4 basically has 42 million transistors. No, and Pentium 4, by Pentium 4 I mean 2000. So nowadays, basically what has happened is the Moore's law. There has been some divergence from the Moore's law, but till from 1971 to basically 2004, it was completely a straight line, and the Moore's law was being followed quite well. So this is about the Moore's law. So this is basically the basic MEMS fabrication process for a layman. So what will happen is, you will have a silicon substrate, you will grow oxide on it, then you will deposit whatever the resistor material which you want, then you will pattern, then you will again add the insulating material which you want, again you will pattern. So you will repeat the cycles again and again, and then you will get the final device. That is how the actual process looks like. So basically, it is the cycle between photolithography, etching, sputtering. Uh, so basically, photolithography, material removal, material deposition, again photolithography, material removal, material deposition. So it's just a cycle that keeps on running, so till you achieve the final object. So yeah, so basically as we said about first thing about the substrate. So basically, how is the substrate manufactured? So basically, silicon is very widely available material. So it is, you can get silicon even in your sea, everywhere you will get it, but that cannot actually be used directly for making electronic devices because of its unique unit cell properties. Uh, okay, so see, cantilever material, for making the cantilever material, it can be any metal per se. So depending on what you are using, so mainly what I would say is we use some piezo resistive material. So basically what is happening is, any cantilever, what you need to do is, you need to the deflection which lead to change in length, and again that change in length has to be will is equal to the change in resistance, and that change in resistance is equal to the force applied. So basically we use piezo resistive material, so that can be like PZT or something like that is basically used, but that completely depends on who is making the um, what do you say, who is making the device. So it can be anything. So there is nothing very specific to the cantilever, but in that problem, what we are saying is cantilever is of separate material. We don't need to bother about what material cantilever is. We only need to bother about the etching of SiO2. So that is all which we need to bother in that particular problem per se. So Shashikal, I think so I answered your question. I'll just continue with the just skimming through. So this is how the wafers are made. This is how the unit cells of so this is how the plane basically is are designated in a unit cell. So basically it is the 110 plane and it is the 111 plane, and uh, the angle between the two planes can be given by this formula. So this is the thing you need to keep in mind, because this thing might be asked again. This is a very important point. This is how the different type of unit cell, the wafer, how they look. So N type, P type is the doping type. uh, so 111 and 100 are the crystallographic plane type. So you need to keep that in mind. So just take a screenshot or maybe just keep in mind. So then again, after that, in that process we discussed, after the substrate is oxidized. So basically for oxidization we have two processes. One is dry oxidation and wet oxidation. So these are the two processes that are used for oxidizing a stuff, um, oxidizing the substrate. So dry oxidation is used for like a small oxide layers. White oxidation is a faster process. It is used for oxidizing large oxide layers. Then after that there is photolithography. So basically this is a spin coating process. So the wafer is placed on a rotating chuck, and then it is deposited with the photoresist, and that is how, depending on the parameters such as the rotation speed and the resist viscosity and other parameters, the resist layer thickness will change. So it takes a lot of time and effort to actually achieve the right properties. So this is how it is. Then after lithography, photoresist is placed. You develop the mask. So once you develop the mask, you wash out the unnecessary area, and then you etch the area which you want to remove. So to use for etching, you need isotropic etching and anisotropic etching. So isotropic etching happens in all direction, and isotropic etching is directional etching. So isotropic etching will be mainly wet etching, and anisotropic etching is mainly dry etching. So this is the etchant triangle. So basically depending on the concentration of etchants, you will get different etch rates. So this is what you can get from the etchant triangle. So basically, as you can see earlier, there were like the acids are highly toxic, so they came up with um, an organic etch, that is tetramethyl ammonium hydroxide. It is like it is low toxic. It is more selective than compared to KOH etching, and it is it has a very good silicon etch rate. So after the entire etching is happened, you need to deposit new material. So for sputter coating, basically what we do is sputtering gas, which is argon, is pushed into the sputter chamber, and then it hits the sputter target and it ejects the target atoms. So and these target atoms then go and hit the substrate and get deposited on the substrate. So in one of the question it is asked, what does sputtering rate depends on? So basically it depends on, so if the distance between the sputter target and the substrate is quite long, the atoms from the target will not actually be able to reach the substrate in high number, so that will reduce the sputtering rate. And again, if the applied power of argon, so if the argon is coming at low power, it will not be able to eject as many atoms from the target material, so again that will also affect the sputtering rate. So these are the process parameters per se for sputtering. So then we came up with the practice assignment. So practice assignment, basically the first was what will be the angle in degree between the two planes, so 1 to 1 plane and 1 0 0 plane. So as I said, you have the formula, so you have to substitute the intercepts and you will get the answer. So this is fairly simple. Again, the second is basically which of this is a isotropic agent. So basically all the wet agents are isotropic in nature, but HNA has very little selectivity compared to the other agent. So here we are selecting HNA as the agent. Here this is the third question. So basically we have to choose the correct statement. So here if we increase the boron doping concentration, the region will act as a mask and it will not be etched away. So basically what will happen is, if the uh, boron concentration is increased, what will happen is it will increase the packing, so there will be more atoms in that region, so it will be difficult for the agent to actually penetrate in that region. So that will basically lead to lower etching, and it can be used in diaphragmatic cantilevers. So that is a true statement. So KOH is basically, yes, the etch rates are different for every etching plane, but it's not that there will be no etching occurring in KOH. So only statement 1 is right. So then we came up with the question 1 from previous year. So here basically we have to calculate the etching time. So we have the dimensions of the cantilever given, and we have to find out the etch rate. So basically we have given two etch rates, the vertical etch rate and lateral etch rate. So basically, since we need to release the cantilever, we need to release the area below the cantilever, etch away the area below the cantilever. So basically the lateral etch rates is what matters to us, not the vertical etch rates. So from that we find out the lateral etch rate, and basically the width, basically since the agent will be acting from both the directions, so the agent from the right will eat away 25 half the width, and agent from right will eat away half the sacrificial layer. So that is why we are sorry for the, so that is how the etching will actually uh, happen. So that is how you calculate the etch rate. So the width, the time, and you get the etch rate, the time in minutes. And since 12.5 the closest is 13 minutes, so we find out the thing is 13 minutes. So again, I discussed this question before. Sputtering rate will depend mainly on the applied power and substrate target distance. Melting point and reflectivity will have no bearing. Again, the next is we have to identify the wafer type. So of n type 111 wafer, again that is this option C. So then we come to the question 4, which is how many atoms are there in the unit cell of silicon. So the answer is 8 atoms. So then the fifth question is basically what are the commonly used p-type dopants. So basically p-type dopants have holes as the charge carriers, and n-types have electrons as the charge carriers. So basically, so for the p-type charge carriers, so only 3 electrons have to be in the outermost shell, so those are from the boron group. And for the n-type, basically they have to have 5 electrons in their outermost shell, that is from the nitrogen group. It's nitrogen, phosphorus, and all the other um, materials from the nitrogen group. So then the sixth question is basically what does HNA stand for in HNA etchant? So basically the answer is hydrochloric acid, nitric acid, acetic acid. And the last question is the seventh question is basically the etching rate is maximum along which plane. So basically, as I said earlier, the lower the atom density, the higher will be the etching rate. So basically, as you have seen earlier, from through 110 plane, the number of atoms are less, so the etching will be faster. If the atoms are more, it will take time for the etching to actually occur. And coming to the last question, basically, what will the resolution be in the photography be limited by? So it will be limited by the only the wavelength of the light. So basically, if the wavelength is quite big, then it will not be able to pass through the micro features in your mask, so that will affect the resolution. The intensity or time of exposure will have no bearing, basically. Okay, so you are asking about silicon nitriding, and so actually every process has a different requirement. So basically silicon nitride is used in different applications, and silicon oxide is used in different applications. Silicon oxide acts as an insulator. Silicon nitride also acts as an insulator, but that completely depends on the application it is. So MEMS is a very vast field, so you cannot actually like just say whether we can use silicon nitride instead of silicon oxide. So the thing is, in theory, yes, you can, but it also depends on the properties which you need from the material. We are not doing like silicon oxide, we are not just doing like for like for in all the devices. So silicon oxide also, basically, why we are doing it is basically, if you have seen a breadboard, so have you seen a breadboard? Basically what happens is, you have a like inside all the conducting wires are there, and then there's a like a insulator kind of material, and there we place all our devices, and then we make our circuits during our practicals. So basically that is the reason we are putting the oxide layer. So basically in the substrate region, we are having all the like conduction happening, and the oxide region is acts as an insulator, separating the completely conductive surface. So basically the entire wafer is completely conductive, so that is why it is used. So silicon nitride can also be used, but again it depends on the application. So I cannot give a definitive answer for your question whether you can use silicon nitride and silicon oxide. Yes, it is used, but it's like it depends on the application. It depends. Sometimes you may not even need to grow an oxide layer, sometimes you can even directly do it, but it is not. But like I have seen one or two research papers where they have done it. I can't recollect, maybe they might have missed that step while writing the research paper, because it doesn't feel accurate, but yeah, it is how it is.
Sir, can you go to slide number 41?
41. Yeah, just a sec. Yeah, yes sir.
That means minimum is 111. Etching rate is maximum along which 110. Minimum will be 111.
111, yeah, minimum is 111. So basically, as I said, the more the atoms it has to remove. So basically etching is basically removing the atoms. So the more the atoms they have to remove, there will be more like more resistance to etching, so the etching rate will be slower, and the lesser atoms you have to remove, the etching will be faster. So that, just keep that in mind. So as I showed you earlier, 110, there are the number of atoms are less along that plane, so 110 is the etching rate is faster.
So 43 PPT page 43, sir.
Okay, yeah. 43. Yeah, yeah, right.
Sir, in this question, okay,
Hmm.
okay, it is wavelength of the light, sir.
Yeah, yeah. So actually, this thing is, so I'll just give you an example. So you have a mask, right? So, so if the wavelength of the light is big enough, so it might, and you have a micro hole which you need to actually get on the substrate, right? Just imagine that, huh? You have a photolithography, you have done the, you have put the resist, then you are using a mask to actually pattern, you achieve your whatever pattern you want on the substrate. So to do that, you have a mask. So basically, if the hole is very small, so if the wavelength of the light is too big, it might not actually pass through that hole. It might just it might not be able to pass through that hole, right? If the wave is too big, it might not pass through that hole. So that is why it might that uh, like it might not that pattern might be missed. So if the wavelength is less, it will pass easily through that hole, and you will get like that feature will be on your wafer. But if the wavelength is quite big, it might not come on your wafer. So that is why the wavelength of light is a very important factor which limits the resolution of the photolithography process. So that is why e-beam and other photolithography processes are being developed. So basically they use electron beam. So basically electron has a very short wavelength. So depending on that, the uh, to achieve higher resolution. So basically in the companies like Intel, they are using e-beam lithography. So to achieve a very you might have seen, if you have bought new phones, you might have seen 5 nanometer processor or something, you might have seen on phone packages or something. So that is why, so to achieve that resolution they use e-beam lithography, which has a very short wavelength. So that is a important procedure, important parameter that affects the resolution in photolithography process.
So this PPT is available in the this one, sir.
So actually if you go to your sorry, just a sec. So if you actually go in your what you say, um, NPTEL portal, down there is live interactive session. So there it will open a Google Sheet. So there you will get all the YouTube links for this live interactive sessions, as well as you will get the PPT for this. So I'll upload this PPT by today late evening, or maybe maximum tomorrow morning. But you will get this PPT tomorrow.
Yeah, this is a very informative. This session is very informative, sir.
Yeah, yeah. But if you need more, I would suggest you just use YouTube. It has everything. It is. I have not touched anything basically.
Thank you, sir. Thank you.
Okay, so yeah, Rajni Ragvi, sputtering rate depends on what? How, sir? Okay, so I'll just go to the side of sputtering process slide. So basically, what we are doing is we are getting the sputter gas. Sputter gas is basically argon. So what is happening is argon uh, is accelerated towards a target. So sputtering target may be gold or any other material which you want to coat on the substrate. So you accelerate argon to the to the sputtering target. Then what will happen is argon will go and hit the sputtering target, and it will eject the atoms of the sputtering target. So basically argon will hit the gold target, and the gold atoms will be ejected, and these ejected gold atoms will be accelerated due to the collision, will be accelerated towards the towards the substrate. So basically RF field will be there in the entire chamber, so that the atoms only go into the straight direction. It won't like, so that the atoms don't go anywhere else. So like a field will be created so that the atoms only go in the straight direction. So here you can see, in this process you can see that there are two parameters that are mainly at like the power with which argon is being applied. So if the argon is applied at a very high power, it will be able to collide very like there will be hard collision between the argon and the substrate target, and more number of atoms will be ejected. You are getting this. One of the main parameter will be the applied power. The second parameter will be the distance between the sputtering target and the substrate. So basically if you increase, so here you are seeing that the gold atoms are basically traveling straight. So from the energy they are gaining from the collision, through that energy they are traveling straight towards the substrate. You getting this point? So basically if the distance between the sputter target and the substrate is increased too much, what will happen? All the gold atoms will not be able to reach the substrate. So the main two properties, main two parameters what on which the sputtering matters is basically the applied power, the power with which argon hits the sputter target, and the other second important parameter is the distance. Basically distance the gold atom has to travel. If the distance is too high, what will happen is it not all the atoms will reach. Some of the atoms might just like not reach the intended destination. So these are the two important parameters that affect sputtering. um, am I is my answer clear, Rajni? Yeah, thank you. So yeah, whoever has any doubts, please ask your questions. In case not, I will not take up your time. You can free to leave the session. Anyone has any other questions? Question 1 of which assignment, practice assignment or the previous year questions? This one or the previous yeah, this one, right? Yeah, so I'll just explain it to you again. So what is happening is you have a cantilever. Cantilever basically it can be of any material, but what is so basically what has happened in this, basically you have a substrate, you have a SiO2 layer. On this the cantilever has been sputter coated. So now what your main aim is, basically you want to remove the SiO2 layer so that you can remove you can like make the cantilever release the cantilever so that the actual cantilever can move and you can do the detection. So now what you are doing is you have an etchant. So the etchant is basically having etch rate. So it is an etchant which has the vertical etch rate of 25 micrometer per minute, and a lateral etch rate of 2 micrometer per minute. So now to release the cantilever, what we need to do? So to release the cantilever, what we need to do is basically we need to dissolve or etch away the sacrificial layer that is below the cantilever. So if the sacrificial layer below the cantilever is dissolved or etched per se, you can the cantilever will be released. So that is what you care. So here in this figure you can see that the cantilever has already been etched from the from its sides, uh, like uh, from its thickness per se. So only what you need to etch out is the width of the uh, um, cantilever. So basically the below part, the bottom part. So now what will happen is basically the agent will be dropped from both sides. So agent will be dropped from the um, along the length of the cantilever. So agent will be dropped from the right side as well as the left side of the cantilever beam. So now which edge rate do you think will matter? So will the vertical edge rate matter? No, right? We need to remove the area which is below the cantilever. So what is lateral edge rate of that agent is all what matters, right? So now from that so now we know that we only care about the lateral edge rate, we don't care about the vertical edge rate. So you am I clear till now? So now the next part is basically calculating the edge width. So basically, as I said earlier, the edge end is coming from both sides. It is coming from the right hand side as well as the left hand side of the cantilever. So now what will happen is basically to eat away the below part. So eat away or etch away the material which is below the cantilever. What will happen is the etchant from um, left hand side will also try to dissolve the material, as well as the agent from right hand side will also act. It will dissolve from the agent coming from left hand side will also dissolve the sacrificial layer, from the right hand side will also dissolve the sacrificial layer. So considering that we are having equal edge rate, so what we will say is, okay, the half of the width is being dissolved by the agent from right hand side, half of the width is being dissolved by agent from left hand side. So the half of the width is what matters to us, and we already I explained you why only the lateral edge rate matters. We don't care about the vertical edge rate. So from that, we are to get the time, basically we get the width what we need upon the edge rate. So that is 25 micrometer upon 2 micrometer per minute. So that is 12.5 minutes. So the closest time is 13 minutes. So that is the answer. So was I clear in this? Anything that was unclear, please tell me. um, Ma'am, am I clear? Was the explanation clear, or do I need to explain it in more deep? Okay, so just imagine this. So this is the cantilever beam, right? And basically, this is the like, just you can just imagine that this is the SiO2 layer, right? So what I will do is I'll the agent will be dropped from this side as well as this side, right? The agent will not just like it will so it's a cantilever beam, so agent will be coming, so you will be depositing agent from this side as well as this side, like you will be so just imagine this way, so you are depositing agent on the right hand side as well as the left hand side, and then the agent will eat up the area from both sides. So like it will eat up, so the agent which you drop this side will eat up the right hand on the right hand side will eat up this much area, half the area at the bottom, and what you drop on the left hand side will eat up half the area. So that is why the width is coming into half. So that is why, so my explanation was basically why the width is 25 and not 50. So for that you use the explanation of terms of right hand side and left hand side. So basically it's you are having both sides, you are having the agent from both coming from both sides. So basically it will be like two circular items. I might, if I can get a whiteboard, I'll just check. Okay, it's clear and it's good because I also don't have access to whiteboard. Any other questions? In case you don't have any questions, you are free to leave because you will. Those who joined in late might have to go through the slides later. So I would not take up your time. So in case you are like if you are done with the questions, you are free to leave. In case of no questions, I'd like to thank you for all for attending the session. Okay, okay. Difference between N type and P type dopants. How do you find out? So like N type is basically it has 3 electrons, as I said earlier. So basically, N type is 5 electrons. Basically, the thing is N type is has electron as a charge carrier, and the P type has basically holes as the charge carrier. So is you need to somehow you have to remember this, that N type is for electron and P type is for is for holes as the charge carrier, and n type will basically be the materials which have 5 electrons in their outermost orbit, whereas p type will be basically 3 electrons, basically because there will be holes, right? So to identify that, um, so uh, all the so with 3 electrons in the outermost orbit, basically it will be the materials from the boron group. So basically it is so basically silicon or carbon will be at the center. So boron, carbon, nitrogen, oxygen, fluorine is how the um, periodic table looks like. So basically carbon and silicon belong to the same group, group 4. So basically all the group 3 elements are basically come into p type, and group 5 elements, so basically that all the elements that come from the nitrogen group belong to p type. And if you want to find out the wafer, basically you need to design your own strategy. Like my strategy basically here is, so for p type 111 is flat is what my strategy is. Then p type 1 n type 111 basically I say is 4 o'clock, then p type 100 is 3 o'clock, and n type 100 is 12 o'clock, is the way I remember it. So 6 4 3 12 is I how I remember them, but you need to find a way out for how you remember them. I hope I was clear with my, like, the difference between n type and p type, both about the dopants as well as the wafer types. How to find out? Basically you need to find out if from the periodic table. Basically you need to actually look at them, you need to go through some literature. There is no trick per se. So basically just you can remember as p type is boron 3 group 3, n type is group 5. So that much I can tell you. Or you can say n for nitrogen and all the elements below nitrogen, you can just remember it that way. But you need to, like, read some theory about it, and then only you will be able to, like, be confident about the p and n type dopants. Okay, so you want to know, like, what is 111 plane, 100 plane, those things. Okay, fine. uh, okay, so basically you can see, you have made a cube out of it. So basically you have a cube. So this is the origin point. So this can be any random point, but this is the origin point. So this is 0 0 0, right? So if we go up only in z, so it is 0 0 a, which is again the just the edge length. A is the edge length or of the thing. So we just for now we'll just consider it as 0 0 1. So this point basically will be 0 1 0, because basically this is the y-axis. So we are only traveling in y-axis, x and z are 0. So this will be 0 1 0. Coming to the x-axis, this will basically we move 1 point, so it will be 1 0 0. So you might have understood till here how the points are given out in this mm, in this entire system, in the coordinate system. Basically how the points are listed. So basically if you go up, it is, if you go in x direction, it is 1 0 0, y direction 0 1 0, z direction 0 0 1. So now accordingly all the coordinates are given, all the points. So this is basically for this to reach this point. So basically what will happen is you go one in so you don't have to travel anywhere in z direction, you only have to travel in y direction, one in y direction and one in z direction. So this is basically 0 1, basically you have traveled 1, and again you have traveled 1 here as well, so 0 1 1. So again like this, here it will be, since you are not traveling anywhere in y direction, here you are only traveling in x direction, so 1 0 1. So in this way you basically get uh, how the coordinates are given. So basically how is the like how a coordinate for a particular point is given here. So now let's come to the family of planes. So I hope you understood how the points are being given, how the points are numbering is happening. So now basically consider this as a plane. So basically what will this plane be? So here the plane is basically you are moving it. So basically this is, so as I said, gave about the points. So basically this is from that you are basically moving a plane. So basically to give out this plane, so what is happening is basically here you are moving the entire base plane by one point. So basically if you are having a plane as like from origin z y, so if you are moving that plane by one unit point, what you will get is if you are considering this as a 0 0 0 plane, you are moving it by 1 point. So this is called as the 100 family of planes. So basically where you have moved the basic uh, like the base plane by one point, you will that is called as the 100 family of planes. Likewise basically in this, basically where you can connect this like all the uh, points. So this plane through the cross section, basically you are getting that is designated as 111 family of planes. So I I I tried. So this is how the planes are being numbered, or how the family of planes is actually demonstrated. You need to go deep into it. Basically, even I am not able to explain it properly because I don't have any slides to show it to you. But you can go on YouTube, you'll find a lot of simple videos explaining that. What is happening is I don't have enough slides to actually explain it to you, and my whiteboard is also not working. But this is some basics of planes. It's how it works. So you just need to go on YouTube and find it out. Maybe next time if you come, I'll just try to put some slides or on this, or else I'll put the link in description regarding the video you can watch for getting more clarity on what the planes are. Okay, so do you have any other questions? number 60. Okay. Yeah, so basically what happens is basically I missed out one step in this process entirely. So what happens is basically after you have oxidized the substrate, so what you do is basically you put the resist on it. So you put a photoresist on the substrate. So you basically put a wafer on a rotating surface, and you just dispense resist on it. So once the resist is dispensed on the substrate, what happens is you get a photosensitive structure on the substrate. So then what you do is whatever the areas you need to keep, you harden them. So basically you expose them to so that step is actually called as photolithography. So you expose that the areas which, so you have a mask. Basically mask has the areas which you need to keep and which you don't want to keep. So the areas which you want to keep, you basically harden them, and the areas which you don't want to keep, you like you just you leave the resist as it is. Then you wash off the resist, photoresist you wash off. So then what happens is then you have the area which you want to remove the material from, right? The material, the area where you want to keep the material, you have already put a hardened photoresist to actually protect them. So after that you etch the areas. So what you do is the next step is basically called as etching. So basically here you can see is basically the yellow in this the gray surface is the wafer, and the yellow surface is basically the photoresist that has been hardened. So the hardened photoresist, so now you have the hardened photoresist and now you want to remove the material. So to remove the material you have two options. So one is basically use the wet etching, or else you use the dry etching. So wet etching is basically using wet, as I say, as the word suggests, is chemicals. Basically, you are using KOH, you are using HNA, you are using hydrofluoric acid, you are using like n number of wet chemicals per se. The second approach is basically using dry etching. So dry etching is basically reactive ion etching. So what it does is basically it is a chamber. So in that chamber there will be some gases that will be flowing through it, and atom by atom it will just take away, it will react with the atom on the wafer, and then through air, basically air will be flowing through it, it will just basically like it will just steal the atom from the substrate, and through air will just like uh, air will be flowing in the chamber continuously. So slowly material will be removed from it. So in dry etching basically only the area that has been selected as you want to keep that area. So uh, you want to remove that area, sorry, the area which you want to remove that area, basically that type of etching is called as the anisotropic etching. And in isotropic etching basically the etching is happening in all directions. Basically it is a chemical doesn't see chemical, basically it just sees the atom, it just sees silicon, or it just sees the atom, and it just tries to react with it, and it just moves away fast. So basically it is called as isotropic etching, is also called as wet etching, in which etching occurs in all directions. In anisotropic etching, the etching only happens in the straight direction, in one direction. So that is called as anisotropic etching. So that is usually dry etching, which is slower and expensive. Isotropic etching uses normal chemicals, it is cheaper, but as I said, it will etch away the lateral part also. So that will again lead to like complications or less accuracy per se. So that is the difference between isotropic etching and anisotropic etching. I hope I was clear with it, or you have some other doubt regarding this slide. Anyone else has any doubts? Yeah, thank you. You can also see the lecture slides later, and I would recommend you watching some YouTube videos because um, basically YouTube has everything. So, anyone else has any doubts? Okay, so then I'll anyway it's 8 o'clock, so we'll just end the session. So I would like to thank you for your attention, and thank you for your questions as well. It was really great. So you will find the recording as I've already mentioned earlier in the public sheet, and you will find the lecture slides by today evening or maximum by tomorrow afternoon. So I would like to thank you all for the session, and I would just end this meeting now. Okay, thank you.